Okay, and everybody can hear me?
Everybody else.
Okay. So my name is Christopher Lozinski. I went back to graduate school here in Poland in Politechnical Silesia. Program is called Microinformatica Systems Cyfrowych in Katowice. It's a free program, what would have been 90,000 or 120,000 in the US. So I'm building a fourth processor. The first soft core is almost done, and then I can do it's kind of all the the boring stuff. And then shortly thereafter, I get to the multi-core stuff, which is much more interesting. Okay, so here's the talk. Let's see. So the first question is, why are we interested in these stack machines instead of just using a Risc-V or some register machine? And the answer is you get much more performance for Forth. So on this table, we have 3 rows for the plus operation, the swap operation, the rotate 3 operation. You can see the stack effect, plus adds the 2, swap, rotate. I'm sure we all know what that does. On a Forth CPU, all of these take 1 cycle. But if you do an ARM, the first one takes 2 instructions, 3 cycles. Next one, 3 instructions, 5 cycles. 3 instructions, 7 cycles. And on the Risc-V, it's even worse because the Risc-V doesn't have any concept of a stack, whereas the ARM and Motorola 68000s do. Okay, so that's one benefit of these. The other thing is we have something called elided words. So I'm beginning to be a Forth developer, and I'm frequently doing dupe to duplicate the top thing. And the reason is the many of the operations they consume either the top 2 items on the stack or the top item on the stack, and so you need to do a dupe. And what the J1 does is it allows you to do 2 operations at once. So you can do a plus, but you can also dupe the second item on the stack, either the first item on the stack with a 2 dupe plus, or the second item on the stack with over plus. This holds true for all of the 2 operand operations. It also holds true for the 1 operand operations and even the 0 operands like reading from memory and so forth. So these are called elided words, and they really speed you up because you're basically doing 2 things at once, whereas on a traditional microprocessor, you could only do 1 at a time. Um, and of course, the interpreter is really great for debugging stuff, but you try to use the traditional interpreter, MicroPython, it's going to take 256 kilobytes of ROM compared to Mecrisp, fits in 11 kilobytes of flash and 512 bytes of RAM. Lua interpreter also takes an awful lot of stuff. Um, the on the FPGAs, the J1 is just smaller on the right third column, right third row, right column. It was only 160 LUTs, maybe 80 LUTs if you just have a 1-bit shifter. The ZPU is kind of the best known small C language stack machine, and it has 442 LUTs. And of course, when they did the J1 video, he did it on a microblaze, which is from Xilinx. In C, it took 16,000 bytes. And on the J1 video application, only took 6,000 bytes. So you save memory, which is very scarce on these devices. You add more functionality. It's just a lot smaller, a lot faster. The worst is if you take a look at the Risc-V instructions. So and maybe it's not quite clear how they're structured, but basically it has 32 registers. So to refer to a register, you have to have 5 bits for the X register, 5 bits for the Y register, 5 bits for the Z register, and then 7 bits for the opcode. That's 22 bits, right? And whereas on the J1, it's a 16-bit, you can do, in fact, a lot of these actually do 8 bits. A lot of these small Forth machines can do an instruction 8 bits. J1 uses the other 8 bits to speed things up. But so it takes up so much less memory than the other solutions. And eventually you get much better concurrency. So one of the huge problems with C is they kind of assume there's a single memory space and you put your data stack, your return stack in there. Okay, you can do a Van Neumann machine where the instructions are separately. You can have your registers separately. Whereas in Forth, you can, have data stacks separately, return stacks separately. Instructions can either be from the single port or remotely. Your data will be in the main memory, but you can do other stacks too. So you can just get a lot more concurrency with Forth, which will lead to faster. So here are last year I did a presentation on reviewing the 66 known Forth cores from the slides. You can click into it. You can click into the video. Really, the J1 is the one that everyone's most popular with. It's very small. It's very fast. It's really quite impressive. Very, very, very intelligently done. But it also has its limitations. It has no interrupts. It has no timer. It has no Forth included. Only had 16 instructions, 8K memory addresses, and requires dual port RAM. We'll get to what that is in a second. So really what you want to be using is Mecrisp Ice. So what he did is he added sort of all the other stuff that you need, he added in. And so that's what I started off using. And there's in fact a huge family of these different J1s, different Mecrisp ones, and it's hard to even understand it. What you need to first understand is what the RAM types are. So we have single port where you can read or write to memory once per clock cycle. You have dual port where you can do two ports can both read and write. And then you have pseudo dual port where one port can read while one port can write during one clock cycle. And the other part you have to understand is the memory. So on the left-hand side, you have the 8K of memory. There are 32 of these small 4K memory blocks, 16 bits each, which gives you 2 to the 8th words. So it comes to 8K words altogether. The newer ICE40s have not only a little bit less of the small block RAM, but they have these huge single port RAMs. So it really behoves the J1 family to upgrade to the new larger open source chips that are available, open source tools. Okay, and now you can understand this diagram because most of the items along the middle are related to 16-bit. Along the bottom, you've got 32-bit, 64-bit devices. Along the top, you have some with a barrel processor, 4 cores running off one ALU. You've got some in VDHDL, some in Scala. So there's a whole family of these, and I'm building a single port one, which is the extension of the family. Plus, there are a lot more forks of the various on GitHub. So there's a whole bunch of these floating around. And of course, the big one is Mecrisp Ice. How does what I'm doing comparing? Well, I've shrunk it down from 2,000 LUTs to 1,000 LUTs. That's speeded up a little bit. Smaller is better. But the big thing is that only uses that uses 30 of the 4K PS RAMs, and I only use 2, and then the memory model is much more. So that frees up a whole bunch of memory. And just to show you how much memory it frees up, you can see on the right-hand side what's actually used by the single port. And all that other memory is free, which means I can do like 4 cores on one of these chips, or I can have multiple stacks, or it opens up lots of opportunity for me. I'll also mention a little bit about the instructions. One of the things that J1 does, on the traditional Forth on the right-hand side, you'll have like a literal, maybe a 15-bit address, and then you have a jump, a conditional jump or a call. What the J1 and Mecrisp do is they put all those into a single instruction. So it limits you to 13-bit addresses, but then the first 3 bits tell you if it's a jump, a conditional jump, a call, or an ALU. So that removes one instruction and speeds you up. Very, very smart. And then I'm using the ICE40 FPGA, which comes on a Pico Ice with an RP2040. Very, very nice board, $35. I'm very happy with it. Beautiful software, firmware. And of course, what I have to do is I have to initialize the single port RAM. And so I start off with a simple core and I copy all the data. The problem is that the large memory blocks can't be initialized in the bit stream from the FPGA. So I copy so I first fire up one core, copy the data into the large items, and then I reboot, and the second core should work. So currently all of these different pieces work. They all work in simulation, but this last piece of jumping from one to the other isn't. But they'll be in a week or two. That'll be working hopefully sooner. So here we have the boot core. You can see on the left-hand side the memory. It reads. It can. There's an I/O block in the middle, so it can read from the shift registers, pull in data. It can. It talks to USB over UART, and can write to the memory. So that's what the boot core does, and it runs off the memory in the lower right-hand corner. And then the runtime core can then boot off that larger memory. And of course, it can now use the 2 little blocks in the upper right-hand corner are the small memory blocks, which it uses for the data stacks. And then the lower left-hand corner, eforth.com, is the terminal emulator. Has really nice for embedded applications because it pauses so it doesn't overwhelm the attached device. And there's a whole Hayes Forth test suite that I have on that too. So eforth.com, great terminal emulator, highly recommend it if you're doing any kind of embedded stuff. Works great. There's the support when you have a bug. He fixes it right away. Just amazing stuff. Really good for embedded Forth development. So I'm, almost done with this. The thesis is partially written. The interesting stuff on the bottom is that I actually did documentation here. Let's see if I can jump to this. Come on. I don't know how to hide my. Well, it's not doing. If you go to Mecrisp-ice dot readthedocs.io, there's documentation on the Mecrisp Ice, so you can read how it does, and particularly the cross compiler is very difficult to understand, and it's documented in there, and you can see all the words and stuff. And that was Mecrisp has this great software, great Verilog, great Forth, tons of it, all kinds of options, as you saw from the previous charts. But it doesn't have good documentation, so I've been adding that. We're doing much better here on time than expected. So lots of skills learned here. Um, I'll take some questions and then I have a few more things to say to fill up the half hour. We can end early, whatever you prefer.
You mentioned so you're using one of the RAM units for each of the stacks. How deep how deep are the stacks?
Yeah, so these are excellent question. These are 256. The BRAMs are 256 16-bit wide. So I can have as many stacks. If you have any need for more stacks, I can give you as many stacks as you want shortly.
Cool.
So for example, the one stack is called a loop stack, right? So then your whole looping becomes a bit faster. And there's some other fun stacks I have planned, but
I'm also fascinated by the logo of the university. Is there some? I guess it's a gear, and then is that some Polish crest or?
yeah, I think the Polish like an eagle or something like that. I haven't paid much attention to it. I'll ask, but yeah, it's certainly a gear on the outside.
It's fascinating the clubs, the clubs on the wings. I wonder some interesting symbology. But anyways,
I'll ask about it. Thank you. Logos are important. If we have a few more minutes, because I'm ahead of schedule, I can say a few more things about what I'm planning on doing in the future, kind of the more fun part. Or I can
Go
take some more
ahead.
questions.
Um, what is the goal? Why are you building this, Chris, if you don't mind me asking? This is Shiva.
Yeah, exactly. That's a great question. This is how software should be. Um, it's not always clear what the end goal is, right? It's just a certain direction. Clearly, Forth is efficient. Clearly, microprocessors are grossly inefficient. They waste so much resources. Clearly, we can do better. There are lots of opportunities for what I can do. In fact, I'm just about to show some of the things I can do here. So let me talk about it. So one of them is multiple cores. So there's this Lattice ICE40 is a very well-known board, very well-known FPGA. There are a ton of boards. It's the open source tools to build it, but you can only fit one or at most two Risc-V chips, and I can easily do. It only took 1,000 LUTs. I can easily do 4 Risc-V chips in here. So that's really quite dramatic because the whole world is going crazy about Risc-V, but it's really very large. Wrong way. Let's see what happened here. Sorry. There's some other boards that have dual port RAM. Once you have single port RAMs, you can actually run 2 cores off a dual port RAM. The statistics are that Forth only accesses memory every 10th instruction or so. And so you can get way more productivity out of your dual port RAMs. Lattice, the people who I'm working with Lattice has a board that has 5 of these larger ones. And so that's great for video. It's got enough memory. And so then we can split up video up into lots of different smaller cores. Barrel processors, the idea is you can have a single ALU and multiple processes. So say you're doing like real-time control where it's not that fast, but you need to be able to. So then what you do is you have a single ALU, and on every clock cycle, you rotate through the ALUs. Each of these slower CPUs can then control one of your IOs. And so for a lot of FPGA devices are built on are for large connectivity, but maybe not so fast signals. And so for this, that works great. Parallax actually does this. They have the propeller Parallax. They've got 8 cores. It's kind of strange. They have one large chunk of shared memory. Each core has only a 512K words of memory. So it's kind of a barrel processor. It's kind of not a barrel processor. There's a new one, Retro Forth, Colin, and their newest version has 8 cores. This is runs on many operating systems, sort of on a single thread. And so you could run something like that here too. Okay, so those are barrel processors. You can do cooperating sequential processors that think transputer or Golang, where the different cores send messages to each other to communicate. Imagine, I think I can play this. Let's see if I can play this. Can I play this? No, I can't play this. But if I go to here, let's do this. You can actually play the video. Here's the ad. So you can do this kind of thing on an FPGA. I don't know if you can see it because they were uploading and downloading. But you can do that kind of real-time vision processing on FPGA, and then it becomes not a hardware problem, but a software problem with multiple cores, hearing aids, sound localization. Okay, so that's kind of the direction I'm going and where I am now. Any other questions?
Could you send a link to that video with your slides? Oh, wait. Yeah,
it's in the
just...
let's see. There's a copy link. Yeah, I sent the slides, but I can put it in the chat.
Yeah, that'd be great.
Escape. Chat. Paste.
Do you want to take a minute and tell us about the COM program? Is it eForth?
Oh, so yeah, eForth COM. So what that does is it does a number of things. One of which is you can upload, you edit and your files on your desktop, but then it's really easy to just upload them. Like you do pound include file name and it uploads, or pound require, which it only uploads if it hasn't been uploaded. And in my particular case, the embedded device was too slow. And so what it does is you put it on half duplex and then it sends a character, it waits for the response. And so in general, it sends a 4th word definition, and it waits for the embedded device to return that the OK dot, and then it sends the next word. Because if you have a large program you're uploading, you could overwhelm your embedded device. So it makes it really easy to do embedded programming. You do it on your desktop, use your desktop editors, but then you can download it really easily to the embedded device. So really, really good for eForth COM. And I think the link is in the slides too. Let's see if I can. If not, you can. Let's see. Go ahead.
Is it a product? Does it cost money?
No, it's free, and it provides great source. Yeah, the link is in the slides too. You just click on the title.
Yeah.
The link for the video is in the slides too. You just click on the title there too.
Just want to be careful when we're touting something to be saying, okay, it's a product, I paid full price for it, so that we don't get flagged as sneaking in a sponsored video.
Oh, I see. No, it's free. It's free. Plus, it gives great support. I mean, you know, and it's open source, and yeah, exactly.
Yeah, there's all sorts of things in the modern age that we have to contend with. So are there any other questions, quick questions?
Yes, I have a question. Have you used Spinal HD to generate the minimal system V to see how small you can make it?
Great question. So if you look at the slides up here on the third one, the one on the top right corner of the ring is actually J1SC, and which is actually written in Scala and Spinal HDL. And so Spinal HDL is one of these tools that generates Verilog or VHDL, and its claim to fame is the Risc-V. So what these guys did is they did a much more flexible CPU than is possible with traditional Verilog. Traditional Verilog doesn't have any of the sort of high-level object-oriented stuff, and so it's extremely interesting to me. And I kind of made I did look at it closely. I made a strategic decision to kind of do as much Verilog as I could, and I'm actually getting to the limits of what Verilog can do. So in particular, I have this bug, and so what I want to do is use one of my working cores on the FPGA with the broken core to debug it. And so I basically have to include two different cores, and they're actually different things. And with Verilog, it's very complex to define two different cores that are almost the same but different. So you have to do all kinds of if-defs, and I've got so many if-defs in my Verilog, it's just miserable. Scala, Spinal HDL, J1SC all solve that problem, and I'm getting very close to needing to move that, particularly when you're doing like lots of cores and you're configuring different cores in different ways and stuff. Absolutely needed. So everyone says really good things about it. Few people are using, but highly recommended. Spinal HDL. Next question, if any.
I'm interested in going the Spinal HDL way, both for Forth and possibly to understand the system V that they do with it. So if you do jump that way, email me and maybe we can, I don't know.
Yeah, so I'm very interested in actually. So if you actually look at the Spinal HDL repository, it's 4 years old, and I've actually kind of updated it. So I'll put my email address in the chat, and if you send me an email, we can follow up on that.
Okay,
Great.
I think at that point we're pretty much ready to move on. Would you surrender the screen, Chris? The next thing on the agenda is the fabulous screenshot. Brad, are you ready to memorialize everybody's ugly mugs for the web?
How do
I am,
stop share?
Yeah, there we go. All right. Is everyone who wants to be on camera on camera?
If you don't want your face on the camera, put your thumb on your lens.
All right. 1, 2, 3, go. All right, I've grabbed a few.
Thank you very much, Brad. I appreciate it. Yeah, I guess. Oh, if you have a background picture, your background picture shows instead of your thumbprint. Okay. I was going to threaten people with recording of their thumbprints, but that probably wouldn't work worth a darn.
That's a bird of a different color.
Yeah. All right. So, OmniChat. Introduce yourself and take.
Okay. Can you hear me? Hello?
Well, I can hear you.
I can hear you.
All right, good. Thank you. Hi, my name is Liang. I'm from Malaysia. So today I'll be I'll need to share screen and just have a look. Okay, so this is my